And it's my great pleasure to start our session of 2025 seminars with a talk of our great friend, very good mathematician, Professor Roland Duduchava from Georgia. Thank you, Professor Roland Duduchava, for agreeing to deliver a talk at our seminar. And please go ahead. Thank you very much.
Thank you for invitation to this seminar, and let me start. I will speak about convolution equations on Lie groups and some applications. First of all, a small survey. I will speak about convolutions on Lie groups, some general facts, then define the spaces, relevant spaces for the consideration of such equations. Then we'll speak about fundamental solutions of differential equations on these Lie groups. We'll give examples of such fundamental solutions. Then we'll speak about examples of Lie groups, and then concrete equations of convolutions, such as Prandtl equation, Tricomi and Lavrentiev-Vytsadze equations. And then I will expose some results about boundary value problems on surfaces with Lifshitz boundary. Okay, and at the end I will speak very shortly about global pseudo-differential operators on one concrete Lie group. What is the main topic of the talk? If we have a Lie group, what it means? It is a manifold with a binary operation. When for the pair, we have the operation for the pairs, and it maps the direct product of Lie groups to itself. We have the unit element, or neutral element is called also, and with multiplication or the operation with this element leaves unchanged the element. And we have also all elements in this group have inverses. It's written here. We will concentrate on the groups which are diffeomorphic with the Euclidean space. There is a diffeomorphism with the Euclidean space. Then, having such a minimal conditions on the groups, it is well known that we have that then the Haar measure defined uniquely. We have Fourier transformation defined on this group, which maps Schwarz space to Schwarz space and Schwarz space of distributions to the Schwarz space of distributions. I will speak about these spaces on the next slide. And this Fourier transform have the inverse, and the Fourier transform and its inverse, they map also these Schwarz spaces to itself. And we have the Plancherel theorem that the Fourier transform up to constant doesn't change the norm of the function. We also have generic differential operators, which are generated by vector fields from the corresponding Lie algebra. I will speak about the examples later. Okay. Convolution operators also. We have convolution operators which are defined as usual, as it is written here. We take the Fourier transform multiplied by some function, which is called symbol of this convolution, and then take inverse Fourier transform. And this maps, yes, this A is the Schwarz distribution. So this operation, the convolution operator defined in such a way, maps Schwarz space of fast decaying functions to the Schwarz space of distributions. And it's defined correctly. This is a general definition of the convolution operator on the groups, and with general symbol of distributional type. Schwarz space and its dual space S prime, they represent pullback spaces of fast decaying infinitely smooth functions, SRM. Since we have the diffeomorphism with SRM, we can define the pullback operators, operator, which can bring the functions on RM to the transform the functions from RM to the functions on the group G, and so we can have then the Schwarz space and the distributional Schwarz space on the group. And as I mentioned above, the Fourier transform on the group and its inverse, they map this Schwarz space of smooth functions and Schwarz space of distributions to itself. Okay. Next, we will speak about convolutions on the groups, about operators. What is important? All generic differential operators, which I told you are generated by the elements of Lie groups, they are convolutions. They are all convolution operators. And their symbols are minus xck. Xck is the independent variable in R. So thus we can solve easily the following integro-differential convolution equations and find their piecewise essential, precise essential spectra. The operators are here, which we can consider. They are convolutions. As you see here, the convolution is defined as the kernel depends on the x multiplied by y minus 1, and the generic differential operators on both sides of its integral operator. And this integro-differential operator is a convolution operator and has symbol which is written here. The formula 1, 2 is the symbol of this operator 1, 1. And it is responsible for the invertibility and the Fredholm properties of this operator. We can formulate precise theorem a bit later. By MPRM, we denote the algebra of functions, LP multipliers, for such that the corresponding convolution operators is bounded in LP space. It's a usual definition of LP multipliers when we have the traditional convolution operators on Rn. But here we have the convolution operators on G, no differences. The same multiplier class works here also. And we have the boundedness of these convolution operators if function is the LP multiplier in LP. And due to the Plancherel theorem, multiplier class M2 coincides with all functions of which are bounded on Rm, essentially bounded functions. They are all multipliers, but only for L2. Functions of Wiener class, which are Fourier transforms of L1, L1, we take L1 functions, take Fourier transforms at constants. Those functions are Wiener class, and they are also not only class, but the algebra. And these are multipliers in all LP spaces. So they belong to all MP. One-dimensional case, in one-dimensional case, all functions of bounded variation are also multipliers. So these facts are well known from the Rm. For the multidimensional case, we have I don't know the precise definition. There are different versions, but I can only define here the so-called polytopes, the piecewise constant functions on polytopes. Polytopes are intersections of finite number of hypersurfaces in RM, and they are depicted here for the three-dimensional case. Those for the functions which are constant on polytopes, and well, on the set of polytopes, they are piecewise constant functions in RM, and such functions are also multipliers in all LP, but P must be between 1 and infinity. They are also multipliers, yes, so such polytopes. It raises a natural question. Yes, we denote those functions by PCRM, and if we close such function in the norm of multipliers, we denote it by PCP RM. Now we have natural question. What is the natural spaces where we can consider these operators? For the usual classical convolutions, we have Bessel potential spaces, which are defined with the help of convolution operators. The same happens here, but we have to define here the convolution, the Bessel potential, generic Bessel potential spaces with the help of convolutions, but on the groups. The definition is absolutely the same. How they are defined? We take function, take the Fourier transform of this function, multiply by xi in power s, it's written here, 1 plus xi squared by power s, multiply with this function, and then take the inverse Fourier transform, and take LP norm. And this is the generic Bessel potential space. Generic Bessel potential space. It's very similar to the classical Bessel potential space, but difference is that we use here the Fourier transform on the group, not the classical Fourier transform, but Fourier transform on the group. And this is very well adapted to consider the convolution operators on the groups. The spaces, generic Bessel potential spaces for the integer n, when the smoothness parameter n is integer, it coincides with generic Sobolev space, GWPN, which is defined with the help of generic differential operators. We take all derivatives up to order n of the function, and then take LP norm. Absolutely the same definition as in classical Bessel classical Sobolev spaces, but here the derivatives are not coordinate derivatives, but generic differential operators, generic derivatives. I have to explain why I call it generic. You know that when some pharmacies, some firma produces some drugs, and then they give the license to another firma, and they produce the same production, but in another factory, then they are called generic. And so the Bessel potential spaces, they are not original, but generic. They produced on Lie groups. And that's why I call it generic. Okay, let's P be between 1 and infinity. The multiplier class for the space GH, Bessel potential space on the group, is independent of the smoothness parameter S, and coincides with the usual multiplier class on LP, MPRM. It's the same as it happens in classical case. So now we consider now here the multipliers of order R. When R is some real number between minus infinity infinity, as the convolution as the symbols for which the convolution operator is bounded between generic Bessel potential spaces Ws and Ws minus R. So it has order R. And this R multiplier class is naturally independent of the smoothness parameter S. And moreover, the multiplier class of order R is the multiplication of the multipliers from LP by Xc power R, where Xc power is here. So it's easy to describe the multipliers of power R. And this multiplier class we need to consider integro-differential operators. Okay, now about the Fredholm properties of the convolution integro-differential operators. Let P be between 1 and infinity, and S be any number, real number. Convolution integro-differential operator, which is here. I repeat this operator when we have the convolution kernel and we have the generic differential operators, and all together this is a convolution operator. And it has symbol, of course. Now, with the symbol which is of order n, this convolution operator is Fredholm in this setting. Then the right-hand side is in generic Bessel potential spaces S minus n, and we look for the solution in the generic Bessel potential space HS if only the symbol is elliptic. Ellipticity means 2, 4, that we multiply it by Xc in power minus S, and this should not be 0. This is the ellipticity condition. It is sufficient. It is necessary condition for the Fredholm property of the operator, but it is not sufficient condition. Here is what is the sufficient condition. If P is equal to, or moreover, if P is equal to, but if P is equal to, or P is not equal to, but symbol is from PCRCP, it is the piecewise constant functions, you remember, closure in multiplier class. In this, for P is equal to, we have no restriction, but for P not equal to, we have to take symbols from PCP. Then the ellipticity condition is sufficient also for equation to have a unique solution or to be invertible, the operator to be invertible. It's also sufficient condition well, it's sufficient, necessary and sufficient condition in these cases. And the operator has only essential spectrum, which is the image of this symbol on the complex plane. We take the image of this symbol, it should be, of course, it's in a scalar case. In a non-scalar case, you have to take, of course, AXE minus determinant AXE minus lambda. So you have this full description of the spectra, but the spectra is essential spectra only. Yes. And the remark here, since we have the Igari paradox, the ellipticity condition, just the ellipticity condition and nothing more, is not is not sufficient for the Fredholm property of equation. And this happens because for P is not equal to, there exist even continuous elliptic multipliers, such that the operator, it is, well, as I mentioned, function is elliptic, but the inverse operator is not bounded. So the operator is not invertible. That's really a paradox, even for continuous functions. Even there exist continuous functions that are not invertible. So that's why we need these restrictions to get a sufficient conditions for invertibility in the case of P is not equal to. Okay. Now, for an integro-differential convolution operator with a symbol from PCP-M, well, of order M, there exists a kernel. Now we speak about fundamental solution. For any convolution operators, has a kernel which is Hermander's kernel, so-called Hermander's kernel, which is a distributional function. And the operator is written as it is represented here in formula 3.1. It's convolution with this kernel. But as I mentioned, the kernel can be distributional function. And this definition can be, well, validated, it's correct. Note that the convolution of distribution with the, because the function is from the Schwarz class of smooth functions, this convolution is defined correctly. Convolution. Yes, Hermander proved this theorem for the classical case, and here this theorem is proved easily because we have homeomorphism with Rn. Distribution of Hermander's kernel of the inverse to a generic differential operator with constant coefficients, which is elliptic, of course. If it is elliptic and it is the inverse operator, we take the kernel of the inverse operator, and we can say that this kernel of the inverse operator is fundamental solution of the operator, fundamental solution. And sorry, I will switch off the telephone. Okay. The fundamental solution also can be represented as the inverse Fourier transform of the inverse symbol. We take the inverse symbol and take the inverse Fourier transform, and it gives us the fundamental solution. Okay. Well, here is just small proof of this. The symbol of the operator has the polynomial growth, and the symbol is elliptic. If the symbol is elliptic, inverse operator is a convolution again with the inverse symbol. Inverse operator has the inverse symbol, and it's convolution. And we take the kernel of it and apply this operator A to it. Of course, it gives you the identity. And since this operator falls on the kernel here, and it gives identity, of course, it is a fundamental solution. You get the equalities that FR, A on FR, convolution with phi gives you identity. That means the AFA is a delta function. So this is a very formal proof of this fact. Fundamental solution, if we have fundamental solution, we can define the well-known Newton's single layer and double layer potentials. And they are represented here. The Newton's potential is when integral taken on the entire omega, which is part of the group, not the entire group. You can take entire group, of course. Then it will be the inverse operator simply. We take the, sorry, here should be, I have written here the convolution on the Rn. It's not right, of course. It should be X group operation with Y minus 1. And then, well, we have these convolution operators. Yes, and the single layer potential is the convolution operator again when the integral taken on the boundary, but the variable is in the domain. And the double layer potential similarly, but we take here the derivative of the normal derivative of the fundamental solution. And this everything gives us layer potentials, and here also is valid Gauss formula 3.5. How to it's kind of well, it's kind of partial integration on the domain. It's well-known Gauss formula. It's valid here for the groups, and it gives us possibility to prove this green formula, first and second green formula, for the Laplace operator, for example. It can be proved for the general differential operators also, but here is presented only for the Laplace operator. This green formula, first green formula is this first one, and the second green formula is the second one here. They are very helpful for investigating the boundary value problems. We will use similar one in our investigation a bit later. First and second green formula. Everything as it is in the classical case works also here. For a mixed type boundary value problem, here it's presented here, we have equation, generic differential equation on the group. And we have the boundary conditions. It's, of course, the omega is the part of the group G, domain in the group. And we have these convolution operators. Boundary value problem for this operator. It's here we have Dirichlet type boundary value problem and Neyman type boundary value problem. Both of them are available, and what we can do for them, we can take a representation formula. We can have a representation formula. Solution to this boundary value problem is represented with the help of the layer potentials. Newton's potential on the right-hand side and double layer potential on the Dirichlet condition and single layer potential on the Neumann condition. And these representation formulas are used then to derive boundary pseudo-differential equation for solving these boundary value problems. I mean, the whole machinery which was working in the classical case works also here. Example of fundamental solution. If we take direct product of half axis R plus N, it is a Lie group with respect to the multiplication with the presented here, the coordinate multiplication, x1 multiplied by y1, xn by yn. And the measure in this group is dx1 on x1, dxn And this is the Haar measure on this group. And generic differential operators here are coordinate derivatives multiplied by the corresponding independent variables, dk multiplied by xk. So we have all necessary operators, and we can for the Laplace, well, how to say, generic Laplacian on this space, when we have this d1 square and dn square sum of the generic derivatives, for this operator, the explicit form of the fundamental solution is presented here in the formula 4.1. So this is the example of fundamental solution on the group. Another example is on the group when you have the direct product of intervals -1, 1. -1, 1 is also a Lie group. I will consider a bit later this group also. But here the group operation is presented here. It's just sum of coordinates divided by x1 plus y1, 1 plus x1, y1, and so on. All coordinates are, well, this is the group operation on this direct product. The Haar measure is dx divided by 1 minus x square. And the generic differential operators here are 1 minus x square multiplied by the coordinate derivatives. And the fundamental solution, Laplacian is, generic Laplacian is this one, as usual. And the fundamental solution is written here, also presented. We can define this fundamental solution not only for differential operators, but also for integro-differential operators. But to calculate, it's much harder for integro-differential, but it's possible. Maybe in future I will get some examples of integro-differential operators and fundamental solutions for them. Euclidean space is the simplest example of Lie group. Here the group operation is just sum. X plus y is the group operation. The neutral element is 0, and the inverse element is -6. Here the usual coordinate derivative is the generic differential operator, and the convolution is the classical convolution operator with the kernel depending on the difference of arguments presented here in this formula. So this is the simplest classical example of Lie group. Another example, also well known, is the convolution on the half-axis. Convolution on the half-axis is also a Lie group, but with respect to multiplication. X multiplied by y is the group operation. And then here inverse is, of course, x minus 1, inverse to x. The Haar measure is dx divided by x. And the Fourier transform on this group is the Mellin transform. Mellin transformation. And we have the inverse and so on and so on. And the convolution operator is the convolution when the argument of the kernel of integral operator depends on the ratio of arguments. And the measure is, as I told you, d tau divided by tau. And the generic differential operators here are, as I mentioned also, the coordinate derivatives multiply the independent variable. So this is also a simple, the well-known example. The third example is less known. That's the interval -1, 1. I also mentioned it above. Here the group operation is x plus y divided by 1 plus xy. And the generic differential operators here are 1 minus x square multiplied by the coordinate derivatives. And the Haar measure is dx over 1 minus x squared. So we have the full full tools for considering this Lie group. Fourier transform is written here, for integral of -1 in formula phi1. I will not repeat. In formula phi1 represents the Fourier transform on the group -1. And it's invariant. It's surprising, but the measure of x multiplied by y is equal to measure of y. But it's, well, and the inverse Fourier transform is presented here. And the convolution operator, now the kernel depends on the x minus y, 1 minus xy. Well, this group operation. Well, Haar measure, so is presented here. Generic differential operator is, I mentioned it, but it's written here, 1 minus x squared by coordinate derivative. So it's an example, non-trivial example of the group. We have also another examples of groups, but I'm not speaking about them. Maybe I will speak about them in details later on the OTA conference in Sharjah. Surprisingly, there are the Lie groups, for example, any star-shaped domains can be considered as a Lie group. Star-shaped domains are all Lie groups. If you introduce the multiplication in proper way, you will get that the star-shaped domains are Lie groups. Okay. Now about examples. First example is Prandtl equation, very well known, celebrated equation of Prandtl, which is called also airfoil equation, 6-1, which is integro-differential equation. It's this equation is convolution equation on the interval -1,1. And symbol of this equation, it's not seen here directly, but after small calculations, one finds out that it is precisely the convolution equation on the interval -1,1. And the symbol is calculated also. It's presented in formula 6-2, C plus 2D xi, ixi, cotangens hyperbolicus, pxi. This is the symbol of this operator. Since the equation is considered between spaces, not in the same space, but between different spaces, from GHS, where you find the solution, to GHS -1, where you have the right-hand side. Then the symbol, which is responsible for the Fredholm property of this equation, or the solvability of this equation, is this one. You have to divide it from the square root from 1 plus xi squared. This is the real symbol, which gives you this equation is uniquely solvable if and only if this function does not vanish. And it's interesting to look on the spectra of this operator. Spectra is presented here. This function is an arc, some kind of arc, and here is presented the case when d is more than 0 and c more than 0. Then it connects these 2 points. When d is negative, it's the lower arc is then presenting the spectra. Of course, if c is negative, then you have to take reflection with respect to the imaginary axis, and it will be on the other side of this imaginary axis. But here I presented only two cases when D is more than 0, C is always positive, and D is either positive or negative. So this is the spectra of this operator. And another equation which falls in this class is Tricomi equation, which was derived by Tricomi about 100 years ago. And it was investigated on the Fredholm property, on the numerical solution, but nobody can solve it precisely until Petrov. I will mention it later. Petrov, and and the solution can be presented now as a solution to the convolution operator. Well, it describes this equation arises in boundary value problems for the differential equations with change type from elliptic to parabolic, hyperbolic one. And then as a boundary integral equation, Tricomi derived this singular integral equation 7.1. The symbol is written here in 7.2, symbol of this equation. If it is elliptic, it depends on the constants, of course, C and D. If it is elliptic, then you can write the inverse operator to it. And here is the spectra of this operator, which is given on this picture. Of course, it's positive C, C and A, C and E. Well, when they are negative, they will be a bit different picture, but it's just an example of this spectra. And the last equation on this class, which I want to present here, is the Lavrentiev-Bitsadze equation, which also arises as a boundary integral equation for the boundary value problem, which changed type also from elliptic to hyperbolic. And then as a boundary integral equation, you get this equation 8.1. They got this 8.1 a bit later than Tricomi. And here the symbol is written in 8.2. And the spectra of this operator has a simpler form. It's this straight line on the complex plane. This is the spectra. Okay. My interest to these equations was attracted by the paper of Petrov and Petrov-Suslina, who applied the diffeomorphism. Diffeomorphism is written here, of the real axis to the interval -1, 1. These functions are inverse to each other, diffeomorphism of the interval -1, 1 to 1. And they applied this diffeomorphism and transferred this equation, these three equations which I mentioned before, Prandtl, Tricomi, and Lavrentiev-Bitsadze. They transformed it to the axis and solved them as a convolution, and they turned out to be convolution equations, traditional convolution equations, and solved them. But they did not notice that you can consider them as a convolution on the interval -1, 1. And my guess was that these equations can be considered as not going to the Rn, on the real axis, but consider them as a convolution equation, so directly on -1, 1. And this approach give many advantages. Well, they consider these equations in spaceless settings and also on W1 setting, the Sobolev space setting, and we consider it in Bessel potential spaces, generic Bessel potential spaces, develop full multiplier theory. We also going beyond this group, we find many examples of such groups, developed the Fourier transforms and convolution equations and generic differential operators and Haar measures for those groups. So this give us possibility to find a lot of similar examples on, and we are now working also on non-commutative case when you have not then the diffeomorphism with Rn, but it's much more complicated case. For example, for the Heisenberg group, but we cannot speak about the results. But I hope that we will get this result soon, and we are working on these problems with my colleagues from Ghent, Michael Różalski, Duvan Cardona, and Arne Hendricks. We are working on these problems. Okay. Oh, yes, I have to mention also Nugzar Shavlakhadze, who also considered with the same approach transformation of this interval -1,1 to the real axis and transformed this Prandtl equation and solved it. And it was independent result from Suslina and Petrov. Okay. Now the application to the boundary value problem on the hypersurface. We have hypersurface in R3. Sorry, I think I have 15 minutes still. Yes, I have
yes,
1 hour.
You have 15 minutes. Okay.
Yes, thank you. We have hypersurface which has Lifshitz boundary. It means piecewise smooth boundary. And these points of discontinuity of the tangent we denote by C1, Cn. And denote it is set by M gamma. Gamma is the boundary of this surface C. Okay, and on this surface we consider differential equation. Differential equation of Laplace-Beltrami. Differential equation of Laplace-Beltrami differential equation. To define Laplace-Beltrami differential operator, we need normal vector field on the boundary on this surface. You know this. This surface, of course, has normal vector field unit, normal vector field nu, which components has nu1, nu2, nu3. And then the Laplace-Beltrami operator is defined as d1 square, d2 square, d3 square, where each of these dg is dg minus coordinate derivatives minus normal component by normal derivative. And the normal derivative, you know, it's not written here, but normal derivative, you know, it's a direct product of, it's a scalar product of normal with the gradient. Okay, and we have boundary conditions also. We boundary gamma, we divide in two parts. In one part we have Dirichlet condition, and on another part is given the Neumann condition with the normal derivative, but this normal derivative is defined with the normal vector field on the boundary of our surface, which we denote by nu gamma, which is normal to the boundary and tangent to the surface. So this is the correct formulation of the boundary value problem for Laplace-Beltrami operator on this surface. Okay. And for this operator, yes, here is the normal derivative on the boundary. You see the normal derivative on the surface is defined similarly, but with nu1, nu-n. And here we have the normal components of on the boundary of the surface. Okay. Poor Neumann and poor Dirichlet problem are particular cases when one of these parts of the boundary where the normal derivatives are given is empty, then you have the poor Dirichlet problem and poor Neumann problem. So all three problems are here, and we can now formulate the theorem, which was proved with my my students, Duduchava and Tsutsunava, that this boundary value problem, it's some kind of generalization of the classical result, that this boundary value problem in this setting which is given here, in classical setting, classical weak setting, has unique solution, but Dirichlet and mixed problem. For the Neumann problem, as in the classical case, you have to add also these sufficient conditions, compatibility conditions, which is written here. The scalar product of the right-hand side with 1 and the Neumann condition, the scalar product with 1 are equal, difference is 0. It's written here. And if f and h are regular integrable functions, then the condition can be written as the mean value of f minus mean value of h is equal to 0. Okay, this is the classical result proved for the surface and Laplace-Beltrami equation. To get more information about the, well, we have now the solvability of this equation, full picture of the solvability, but in weak classical case, weak classical formulation. What about such formulation to get deeper results than when look for the solution in generic Bessel potential spaces? And the right-hand side is also general Bessel potential space, and the also the boundary data are also in generic Bessel potential space, formulated here in 10.3, with weight also. And the generic Bessel potential spaces here on the surface and on the boundary and so on, and with weight, are defined locally. I will not dwell on this now. To the set of knots M gamma, we add also the smoothness points on gamma. We adjust the Dirichlet and Neumann conditions collide. If the Dirichlet and the Neumann conditions collide on smoothness points, we also add to the knots. And now we have such classification of knots. MDD is the knots where the Dirichlet and Dirichlet conditions collide. MDNN is the points where they collide Neumann conditions. MDN is the set of points where the conditions Dirichlet and Neumann collide. They can contain smoothness points also. Okay, to each knot CG, we associate a model domain, just angle, infinite angle, with straight, how to say, sides, and straight rays, and magnitude of the same magnitude as this angle had on this surface. It's well, we just take in correspondence to such point, such angle. If we had the smoothness point, then it will be the half space, of course, because the angle will be P. And we have to formulate here 3 model problems. In such model domain, we formulate Dirichlet problem, when on both sides, on both rays are given Dirichlet conditions, or on both sides are given Neumann conditions, or in both sides, in one side is given Dirichlet condition, and another side is given the Neumann condition. And of course, we consider it generic Bessel potential spaces. So now we can formulate the theorem that local principle, the initial mixed boundary value problem, in the non-classical setting is Fredholm if and only if all model problems are Fredholm. all model problems in all nodes. In points where we have smoothness points, we don't consider them because there is a trivial solvability holds there. But for nodes, we have to consider these boundary value problems carefully. And the solvability of those problems gives you solvability of the initial problem. If one of them is not Fredholm, then the initial problem is not Fredholm. The initial problem is Fredholm if and only if all these model problems are Fredholm. And we can speak about also about solvability because we had the solvability in the classical case, and then we can conclude some solvability not only Fredholm but property, but the solvability of the initial problem. And here is formulated the conditions in the generic Bessel potential spaces. What are the conditions for this solvability? And this formulated in formula 10.7 for the Dirichlet conditions, where they collide in CG. For the Dirichlet-Neyman points, we have the 10.8, and the Dirichlet and the mixed problem, we have 10.9 conditions. As you see, these conditions are very explicit. Only parameters of the space and the angle are participating here, non-irrational functions and so on. And this happened because we consider this problem in generic Bessel potential spaces. At the beginning, me and my former PhD student Duduchava considered it in classical Bessel potential space. And then theory was much more complicated, and the answers were not such nice answers. We had some sinuses and cosinuses should not become zero, and you had to calculate them, and you never get the exact answers, only approximate answers. But here in the generic Bessel potential spaces, we have a very precise answers for when these problems are Fredholm and also solvable. I don't formulate here the solvability conditions, but they also exist. And how it is done? We reduce this integral model problem to the boundary integral equation on the half-axis. And these integral equations are presented here 10-10. It's a 2x2 system. And the convolution operators presented there, they are convolutions on the half-axis, Mellin convolutions. And we calculated precisely the symbol, and the determinant of the symbol is not zero, is necessary and sufficient conditions for the Fredholm property. And from this, we derive these explicit conditions. That's only for the Dirichlet points, but Dirichlet-Neyman and Dirichlet-Neyman points, everything is done in the similar way. Of course, we have different equations, because and that's why we have different answers also. And for pseudo-differential operators, if we take the direct product of -1, 1, it is direct product of n samples of the -1, 1. We can consider the pseudo-differential operators on this Lie group. For these pseudo-differential operators, it's non-published paper, but submitted for the publication with my colleagues, Duan Cardona, Arne Hendricks, and Mikhail Ruzhansky from Ghent University. We proved all classical theorems for the pseudo-differential equations, such as L2 Pfefferman type estimates and Calderon-Vaillancourt theorems, formulas for the composition, Goldberg-Lemon compactness of the operators, new theorems on the boundedness of such pseudo-differential operators with piecewise constant functions, I mean, on these polytopes, and so on. We prove also Atiyah-Zinger, Fedosov index formula for such elliptic operators with matrix symbols from the Hermanders class. And this, well, the full theory of pseudo-differential equations. And here is the literature which on which is based my talk. Thank you. And if you have questions, I will answer with pleasure. Thank you.
Thank you. Thank you very much, Professor Duduchava. We have time for questions. So please, if there are questions.
Alexey, I have some comments.
Okay, please.
So, I know on this work of the Roland maybe 2 years ago, it was very interesting. It was very interesting approach to new theory of partial differential operator with bad boundary. So the situation, so the investigation of the boundary value problem, it's clear in the case of the smooth case, we have the some canonic problem. First, it is a canonic problem is some problem in the half space. In other case, the canonic problems for the Kondratev theory and much more, it is the investigation of the conical points, and we have, in this case, we have convenient the some canonical operators. This operator in the cone is connected with the Mellin transport. So
Yes.
I understand, as I understood the Roland paper with him past essays, so he proposed much general case when we have the canonical operators. If the operator is connected with the operators on the some on the canonical operator is connected with some commutative groups, and we see a very interesting example of this group, differential and pseudo-differential operators in this group. So it is this operator is locally representative in the general theory of partial differential equation. It's allowed to consider many interesting cases. Is Dirichlet-Neumann problems, the problems with the singularity, and many other problems. So also it is also the application and new theory of the pseudo-differential operator. So it's very, very interesting. For me, it's a new step in the theory of boundary value problem and pseudo-differential theories. Thank you very much, Roland.
Thank you for this comment, Vladimir. I think we can think also about the Kondratev's result on cones to consider in the sense of these groups, because the cones are also Lie groups. Cone can be considered as a Lie group, and maybe this approach will bring some new, new lights on these equations. It will be interesting to discuss it with you.
Okay. More questions? Well, maybe I'll have some questions. Roland, as I understood, and we already spoke about it on the conference that in the case of interval -1, 1, when you have a Haar measure, you can go from interval -1, 1 to real line and forth and back.
Yes.
And that's appeared in papers by Vladimir Petrov and Tatiana Suslina, and basically you can just reduce this case to convolution case. If you have a measure which is different from Haar measure, then you need to stay on the interval and you need to solve the boundary value problem or equation from the scratch by maybe similar technique, but you cannot just go to real line and take results from real line. So you have to stay on the space, right? So that's how you do this, right?
Well, if I understand correct, you mean that when we have different measure on the -1, 1, yes?
If you don't have a Haar, if you have a general measure, which is not Haar measure.
No, well, you know, then you have not Fourier transform.
Yes.
Because the Haar measure is a uniquely defined measure.
Yes.
And it gives you Fourier transform. If you have different measure, I don't know, then you have not Fourier transform. The convolution will be different.
That means that there are no such results in case of general measure, right?
It complicates things very much.
I see.
Yes.
I see.
Yeah.
Okay, well, maybe one more question. You remember I also mentioned that this transformation that you and Vladimir Petrov and Tatiana Suslina used in the interval -1, 1, this is just restriction of Möbius transform from the disk. Sorry, I just need to. It's just restriction from Möbius transform from the disk. Maybe did you see any kind of equations in complex setting in the unit disk, similar equations with similar technique? Because I didn't see such kind of equations, such kind of results.
Sorry. Repeat, please. I cannot catch your question.
Okay, I mean that, again, back to this case studied in papers by Petrov and Suslina, interval -1, 1, Haar measure, and then is this transformation that is automorphism of the interval -1, 1.
To the axis, yes.
No, not to the axis. You stay in the same interval -1, 1. You use this automorphism that gives you convolution. That gives you the convolution. This is particular case restriction on the real line of a Möbius transform. That is automorphism of the unit disk in complex plane. That's why I wonder maybe there are some analogs of these famous equations in complex setting, in complex variables. I didn't see, honestly, such examples, but maybe you saw some kind of examples.
I cannot say anything definitely in this case. Of course, one should consider. Maybe it's interesting, of course, but one should try. I never tried. Sorry.
Okay. It was just a general wondering. Okay.
Yeah.
Well, maybe some more questions. Well, I don't see hands. We had very detailed.
Можно я по-русски спрошу?
Ради бога, пожалуйста.
Окей, Володя.
Можно и по-грузински.
Хорошо. Я уже спрашивал вас этот вопрос, когда вы в Ростове рассказывали. Может быть, появились какие-нибудь приложения многомерных случаев?
Так.
The question is about applications in multidimensional cases.
Multidimensional case. Подождите, какие приложения вы имеете в виду? Я не понял, извините.
Ну, вы рассказали, вот там уравнение трикоми, уравнение Пиранки, Лаврентьева Бета. Это все одномерные случаи. Это вот то, что было в наших статьях.
Известно от Петрова еще, да.
Да, ну вот я и есть Петров, поэтому...
Извините. Да, от вас известно.
Вот, да. Так я хочу узнать, может быть, у вас есть приложение многомерных случаев?
Нет, к сожалению. Но вот сейчас как раз мы вот вопрос Рабиновича был, что об уравнениях в конусах, который рассматривал Кондратьев, вот там может быть вот для таких дифференциальных уравнений вот в многомерном случае можно будет это реализовать, но не дошел я до этого еще. Будут интересные случаи, я обязательно напишу вам.
Потому что у меня вся эта наука появилась именно от приложений. На самом деле от уравнения трикоми.
Ага.
Вот получилось написать уравнение трикоми как уравнение свертки, ну и дальше появилось само преобразование.
Да.
А у вас идет от общей науки, да? Вот на самом деле хочется приложений.
Ну, приложение такое, что мы развили это не только для группы -1,1, а развили, например, для группы, вот если взять любую звезднообразную область, это тоже группа. Для него тоже мы выписали преобразование Фурье, свертки и так далее, и написали дифференциальное уравнение. И ну, конкретно из приложений мы сами ищем такие уравнения, чтобы вот как на каком-нибудь сложной области, чтобы она попала под вот такие свертки. Но пока у нас нету, но мы тоже очень заинтересованы. Есть какие-то, в общем, я посмотрю, если что-то такое найду, обязательно свяжусь с вами, но мне нужен ваш мейл, по-моему, у меня вашего мейла нету, но я найду, в общем.
Хорошо, ну, у Алексея можно спросить, я могу вам прислать.
Я пришлю.
Да, пришлите, пожалуйста, нам нужен контакт, потому что мы так занимаемся такими вопросами, которые близки друг к другу, конечно. Да.
Хорошо, спасибо.
Да, и спасибо вам большое за эту догадку перевести вот эти уравнения трикоми на отрезок, на отрезке, на R, который мне дал эту идею, что рассмотреть это как группу -1,1. Это, так сказать, я же сказал, это как раз меня привело к этой идее ваша работа.
Спасибо большое.
Okay, well, maybe more questions. Well, we had very good discussion, very nice presentation. After that, we had very good discussion. So let's thank speaker for very nice presentation.